Hello everyone, my name is Mike and I am sharing my top 10 techniques for improving your group delay measurements on devices under test that have frequency conversion and embedded local oscillators. For example, something like this, MyTech satellite block down converter. This is a device that has a 20 gigahertz input and it down converts the signal to about a 1 gigahertz output, and it uses an embedded local oscillator operating at 18.75 gigahertz. So for a device like this, I want to measure its group delay. And I'm going to share with you my 10 techniques for making the measurement as accurate and as easy and fast as possible. And of course, for my measurements, I'm going to use the Rohde Schwarz ZNA Vector Network Analyzer. This is an instrument that we introduced to the market about 1 year ago, and we optimized it for making measurements on frequency converting devices. In particular, I'm going to use option K9, which is our two-tone technique for measuring group delay on frequency converting devices. Now, for more information about that technique, we have an application note, 1EZ81, which is for making group delay measurements on frequency converting devices. It describes all the technical background that you need for this measurement, including the equations and what's happening behind the scenes. But we're not going to read the application note right now. We are trying to optimize different settings in real time. We want to see the effects on screen while we make the changes. So, as I said, I have 10 techniques, and in this video, I'm going to go through technique number 5. Now, this technique is select the best or optimize the IF bandwidth setting of the instrument. Now, just as a review, so far, we decided technique number 1 was to automate your measurements so they're always repeatable and they're documented. Number 2 was to pick the optimal way of combining or creating a two-tone signal for your particular setup. Number 3 was to optimize the power levels, okay? This is where we brought the power of the second tone up, so it was equal to the first tone in power, and we got the best signal-to-noise ratio on the receiver. Number 4 was optimize the tone spacing. That's right. And now we're on to optimizing the resolution bandwidth setting of the instrument. So, following on what I did before, I'm going to use these script files to create multiple channels with different resolution bandwidth settings, and then I'm going to calibrate all the channels with the exact same conditions so we can see right away what the difference is as we change the resolution bandwidth. So let's do it. We'll start from a preset condition. I'm just going to make sure this GPIB Explorer tool, I'm going to close it so we really start the same way every time. And the way we get to this GPIB Explorer tool is we go to the application key, we press GPIB Explorer. It launches the tool. We make it full screen in this second window, and then I can do File, Open, and select the script I'm looking for. So in this case, it's number 5, optimize the bandwidth settings. We say OK, and this script creates 4 channels for us, and then it calibrates all 4 channels under the same conditions, and each channel has a different resolution bandwidth setting, so we can see directly what happens for the different settings. So, it's going through the calibration step right now. Okay, and now it's done. We can say okay. Now, as I mentioned, it's 4 different resolution bandwidth settings. Everything else is the same in these 4 channels. So we just see the impact of the resolution bandwidth. In this upper left corner, this is using a resolution bandwidth of 50 kilohertz, and we can confirm that by going to the bandwidth key. And when this channel is highlighted, it shows 50 kilohertz. The second channel is using 10 kilohertz. Third channel uses 1 kilohertz, and the fourth channel uses 300 hertz. So we see right away the effect as we narrow up the resolution bandwidth. The first channel has a peak-to-peak variation of about 700 picoseconds, so it's a wide IF bandwidth. It's a very quick sweep, but a little bit noisy. The second channel at 10 kilohertz has a peak-to-peak variation of 300 picoseconds. By the way, this 10 kilohertz is the default setting, so this is what has been used in all the videos up to now. So this is taking advantage of everything we learned up to now. And we saw at the end of our last video about 300 picoseconds peak to peak. So this is where we were. This channel is using a 1 kilohertz resolution bandwidth. And now the peak to peak variation is less than 100 picoseconds. We're down into the 60 or 70 picosecond area. Now it's a little bit slower sweep. You can watch when it gets to this channel how quickly it sweeps across. So it's a little bit slower, but is it worth it? Well, we certainly improved our peak-to-peak noise variation, so I think it is. Now in the fourth channel, we're down to 300 hertz for resolution bandwidth, and now our peak to peak is about 40 picoseconds, half as much as it is over here. So we are getting to the point of diminishing returns, going of course from a peak to peak of 500 picoseconds down to 75. This was really worth it probably. Maybe this is going too far, but this is one of the things that you will need to evaluate or decide as you're trading off sweep speed versus trace noise. But certainly this is idea number 5, where we can get down to a much lower trace noise during our group delay measurement just by narrowing up the IF bandwidth. And if you want to compare the different bandwidths, this is how easy it is to do. We're in a script file with a bunch of different channels, each one with their own bandwidth. We calibrate them all at the same time, and then we directly compare apples to apples on each channel. So I can tell you now what I'm going to pick for going forward with the rest of the videos is a 1 kilohertz resolution bandwidth. So this is my new setting, but we're not done here. There's more things we can optimize, and so in my next video, we will optimize the next thing to get this peak-to-peak trace noise even lower. That's right, even lower.